We have one more model that we're going to look at now. It's another example of a system of difference equations. And this one is going to be a one that you can use to study how populations of different species interact when one of the species is the predator and the other is the prey. These predator and prey models are very commonly used in biology. And one of the first and most famous ones was proposed by Lotka and Volterra. And so sometimes you'll hear these described as the Lotka-Volterra model. But they fall into a more general class of just predator-prey models. All right. And so as an example of this type of model, we're going to consider two species. We're going to have squirrels and hawks. And squirrels are the prey and hawks are the predators. Now, the way that we're going to think about this is squirrels, they eat primarily plants. And so we don't necessarily need to worry about them having not enough food because plants are pretty abundant. And so we'll essentially assume that they can grow, their population can grow as quickly as it needs to. But the hawks, on the other hand, they're limited by the fact that they depend on the squirrels for food. And so their population can only really grow if they have enough food. All right. So hawks and squirrels, their population levels are going to be interdependent, and we'd like to model how one affects the other. And the general framework that we're going to use is the same as always. We're going to take the new value and express it in terms of the old value and the change. And we're going to then work on describing the change. And those changes can be described mechanistically in terms of the individual events or interactions that lead to changes. And so we need to think about what types of events cause the squirrel population to change and the hawk population. And there are a few things that come to mind pretty quickly. The first is, well, squirrels can be born. And if you're trying to model births, the simplest assumption you might make is that the number of births is proportional to the size of the population. The more squirrels you have, the more squirrel babies you have. And so we'll introduce a proportionality constant. We'll call that beta S. So there's our proportionality constant. And you can think of that as the birth rate. How many births would we expect to have each unit of time for a given squirrel, right? Presumably it's going to be some relatively small number if our units of time are days, but if we're looking at years, potentially we could have many offspring for each squirrel. All right, so squirrel births is one way that the population could change, and that would obviously increase S by 1. We could also have squirrels die, and they could die due to natural causes, or they could die due to predation. In terms of natural causes, you would expect that to not be affected at all by the hawk population, but the more squirrels you have, the more likely that any given squirrel, that a squirrel will die. And so the number of squirrel deaths should be proportional to the squirrel population. And so again, we'll have a proportionality constant delta S for the death rate. But when it comes to deaths due to predation, this is going to be a little more complicated because there are multiple factors that affect this. First of all, the more squirrels you have, well, the more likely, the more deaths you'd expect to have due to predation, right? Lots of squirrels means lots of squirrels that could be caught by the hawks. On the other hand, the number of hawks should also matter, right? If you have very few hawks, then they're not going to be able to eat many squirrels, but if you have a giant hawk population, then they should be able to take care of the squirrels very quickly. And so because both of those matter, we might assume that the number of squirrel deaths is proportional to both H and S. So we have a proportionality constant CS, and that's multiplied by the number of hawks and the number of squirrels. Okay? All right, so that takes care of changes in the squirrel population. Let's now move on to the hawks. As before, we can have hawks that are born, and in a vacuum, you might assume that the number of births is proportional to the number of hawks. Again, more hawks means more hawk babies. But given that we have these constraints in terms of their prey, you might modify this slightly to account for the fact that we really can't have the population growing if S is 0, right? If there are no squirrels. And so I'm going to add a term to this, which is going to account for the fact that the more food that's available, the higher the birth rate we would expect to have. And similarly, the less food that's available, the lower the birth rate. So because the interactions between hawks and squirrels are proportional to h times s, this adjustment to the birth rate is also going to be proportional to h times s. Or you could also think of that as just the birth rate is beta h plus ch times s, all times h. So I've just factored out an h there, and that's just saying the more squirrels we have, the higher the birth rate is going to be, where this is the effective birth rate. And beta h is basically the baseline birth rate. It's the birth rate in the absence of food. Okay, so that takes into account births, and then we also have hawks dying, and in this case, hawks don't have any predators, and so they will only die due to natural causes, and we might model that exactly like we did the squirrels, assume that's proportional to the number of hawks. All right, so we've got 5 different types of events or interactions that can cause changes, and notice the first one, that would increase squirrels, the second one would decrease squirrels, as would the third. And so those 3 would all show up in the equation for delta S. And then the last 2 would show up in the equation for H. So births obviously increase and deaths decrease. And so that will dictate the signs that we include with each of these individual events. All right, so if we want to put everything together, we could say that the new values of our 2 variables has got to be equal to the old values plus, well, the change. And the change we said would be due to births, deaths, and deaths due to predation. And notice again, I put the signs in so that the things that increase the population get a plus sign, the things that decrease the population get a negative sign. And for the second equation, we would have beta h times h plus ch times hs minus delta h. All right, so there's our model describing the change in both populations. And again, like our epidemic model, this is a nonlinear equation. And I've been leaving off the subscripts here, so let me put those back in. Each of those should be at time n. And the net result is something like this. And we would like to be able to find a solution for how those quantities vary over time, but because it's nonlinear, an analytical solution is not likely to be possible, and so we will opt for a numerical solution. Now, the challenge is we don't actually know the parameters here, and there are a lot of them. We have beta S, we have delta S, we have CS, we have beta H, we have delta H, we have CH, and then we also have initial values. How many squirrels did we begin with? How many hawks did we begin with? So there are actually 8 different parameters that we would need to know to be able to actually describe this system and say exactly what we think is going to happen. And estimating many of those things would be difficult. You could imagine doing a little bit of research to see if biologists have estimated birth rates and death rates for squirrels. But my guess is that's not going to be readily available information. And so most likely what you'd have to do is fit this to the data. But what we're going to do is we're going to actually, since we don't know exactly what the value should be, we're just going to explore, we're going to perform a sensitivity analysis to see how the behaviors vary as we adjust our parameters. All right, so again, you could solve this numerically using MATLAB or Octave, using a very similar framework to our epidemic model. And if you do that, you might get a plot like the one I'll show you in just a moment. And I guess I'll mention this one more thing. You may notice that you can't actually reduce the number of parameters by recognizing that beta S and delta S could be factored out. And the same thing would be true of beta H and delta H. We could factor out an S and an H there. And you know that because of that, essentially only beta S minus delta S appears. They always appear together. and the same thing with beta H and delta H. So if we wanted to reduce the number of parameters, we could certainly do that, and just define a new parameter that is just the difference between the birth and death rates. And as a result, that would get us down to, well, at least 2 less parameters that we have to worry about. All right, on to the numerical solutions. So here's an example where we've started both populations off with a relatively low value. So there's not a lot of squirrels, not a lot of hawks. And you'll notice that there's a story to tell here. Initially, the blue curve, which is the squirrels, grows very quickly. And it looks like exponential growth. And I think you will indeed find that that's the case. But as the squirrel population grows, what's going to happen? Well, if you recall that the hawk births had the form beta H plus, I think we called it CHS times H. So as the number of squirrels increases, the hawk birth rate increases, and so the hawks are going to start to grow in population as well. And somewhere around here, we see that the hawk population takes off and grows very, very quickly. Well, what happens when there's lots and lots of hawks? Well, they eat lots and lots of squirrels, and so soon the squirrel population is going to take a dive, and ultimately in this scenario, the hawks will drive the squirrels to extinction. There are no squirrels left, and once the squirrels have died out, the hawks, well, they have no food, and so they're gradually going to die off as well. And so this is a sort of very dark scenario where both populations go extinct due to the fact that the birth rates for the hawks was so large that it ultimately resulted in extinction for their food source.